Angular motion. Linear motion in a straight frame of reference can be correlated to angular motion in a rotational frame of reference. For example, the linear quantity of position correlates to the angular quantity theta. Velocity correlates to angular velocity, and acceleration correlates to angular acceleration. We also learned earlier this week that time correlates to period. So all of these equations are ones that you've seen before. These are different forms of our kinematic equations using velocity, acceleration, time, and position. When we're in a rotational frame of reference, we can use the same equations. We just have to consider them using our angular variables. Angular displacement is represented by our Greek letter theta. It's the angle of a circle measured by a reference line where theta equals 0. In this diagram, theta equals 0 is right here at the x-axis. Theta, or angular displacement, is measured in radians, degrees, or revolutions. One revolution, which is all the way around the circle, is 360 degrees, which is represented in radians as 2 pi. An angle of 1 radian is 57.3 degrees. A radian is defined as the point where your arc length s is equal to the radius r. The standard unit of angular displacement in physics is radians, so we're going to be doing our calculations in radians. Angular velocity is represented by this symbol here, which is the Greek letter omega. Angular velocity is the rate of angular displacement, which is why you can see here, it's the change of angular displacement over time. That's the rate of angular displacement. When you're going around a whole circle, that means that your angular displacement is 2 pi radians, and the time it does so is 1 period, which is why you can set that equal to 2 pi over period. This line here over the omega is indicating that it's the average angular velocity. The unit for angular velocity is radians per second, which makes sense because angular displacement is measured in radians and time is measured in seconds. You can also use revolutions per minute, or RPMs, but they need to be converted into radians per second for physics calculations. This picture shows something with a small angular velocity. You can see that in 5 seconds, it's only gone a quarter of the way around the circle. This second picture shows something with a large angular velocity. You can see that in 5 seconds, it's traveled farther, making it halfway around the circle. So you can see it's traveled a larger angular displacement in the same amount of time. Down here, you can see that a counterclockwise rotation is positive, and a clockwise rotation is negative. You've totally seen this before because as you rotate something counterclockwise, you're moving it left. So that's lefty-loosey. When you loosen something, it rises upwards, which is positive. Whereas if you rotate something clockwise, you're doing so righty-tighty. And by moving it right to the right, you're moving it clockwise, and the object is moving downwards or tightening. So that is a downwards or negative motion. The idea of righty-tighty, lefty-loosey is given a name in physics. It's called the right-hand rule. In the right-hand rule, your fingers are going to curl in the direction of rotation, and your thumb will give you the direction of the angular velocity. So if you wanted to tighten something down, you would rotate righty-tighty, and your thumb would point downwards on your right hand, indicating that that is a negative action. Whereas if you wanted to loosen something, you would rotate it counterclockwise, lefty-loosey, and in doing so, your right thumb would point upwards, showing that that is a positive motion. This right-hand rule is also used for other things in physics, such as the direction of current flowing through a wire. In this example, an old phonograph record is rotating at 33 1/3 RPMs. We're going to convert its angular velocity into radians per second. It's important to note that RPMs is representing revolutions per minute, with revolutions on the top and minutes on the bottom. So if we were going to convert this into radians per second, we would want to cancel out the revolutions, which is going to leave us with radians. And then we want to cancel out the minutes, which would leave us with seconds. I got 3.49. Now the answer listed technically says that it's negative 3.49, and that's because I forgot to say in the problem that phonograph records are going to rotate clockwise. Let's try this next one. It says if a CD rotates at 22 radians per second, what's its angular speed in RPM? You would start with 22 radians per second. Fill in your conversion, and then you actually have to be really careful when you type this into your calculator, because the answer is 210 revolutions per minute, but some people will get 2073, and that depends on how you enter this into your calculator, depending on the order of operations. So if you type in 22 times 60 divided by 2 pi, you'll get this. And if you type in 22 times 60 divided by 2 pi, you'll get this. And that's because when your calculator sees you dividing by 2 pi, it doesn't know what to do, and it thinks that you want this, putting pi in the numerator instead of in the denominator. So just be careful that when you're dividing this, that you put parentheses around that 2 pi. Tangential velocity. Every point on a rigid rotating body will have the same angular velocity. That means that this point might be revolving at 1 revolution per minute, and this point will also be revolving at 1 revolution per minute. These points, however, will have different tangential velocities. Here's the equation to represent that. Tangential velocity equals distance over time. For an object moving in a circle, the distance it travels is its circumference. So if an object travels a whole circle, or 2 pi radians, in a certain amount of time, that's equal to its angular velocity. So we can say that multiplying the radius here by the angular velocity will give us its tangential velocity. And what this implies is that on a circularly moving body, that 3 different points here would all rotate in the same amount of time, for example, 1 revolution in 1 minute. However, the point at the very center would make a small circle in 1 minute, whereas this point and this point would make a larger circle in 1 minute, meaning that they're covering a larger distance in the same amount of time and giving them, therefore, a larger tangential velocity. This happens on merry-go-rounds in the park. So on a merry-go-round, if you were standing in the very center, you would rotate around in the same amount of time as someone standing on the end. And you would end up, like, for example, looking at the same point off in the distance at the same time. However, the person on the outside would be moving far faster than the person on the inside. And the person on the outside would be, for example, hanging on for dear life, while the person standing on the inside might be doing so happily. This is a Calvin and Hobbes comic about the same topic. It's really interesting because of the implications of the music on a record. So on a record, a needle reads the grooves in the record, and the grooves here at the beginning are moving a lot slower, and therefore can hold a lot more information than the grooves at the outside. So that means that the interior, or the very first songs on a record, can be more musically complex than the ones on the outside, because they can hold more divots and more bips and bops and more information per second. This is why singles are usually placed at the beginning of a record rather than the end of a record. because they just sound better. Angular acceleration is represented by the Greek letter alpha, and its equation is alpha equals delta omega over t, which means acceleration equals velocity over time. Since the velocity is measured in radians per second and the time is measured in seconds, that gives us an acceleration unit of radians per second squared. You can also represent angular acceleration this way, being synonymous to saying velocity equals initial velocity plus acceleration times time. This is just written in a linear reference frame, and this is written in a rotational reference frame, but they're used the same way. Here's what's up with the direction of angular acceleration. When an angular velocity and acceleration have the same side, the speed will increase. For example, if you look at these two objects here, this one is moving forward or rotating counterclockwise and speeding up. These are the same sign, positive and positive, which gives a positive angular acceleration. Whereas if you're moving backwards or rotating clockwise and you're slowing down, these are the same sign and they're both negative, which means that your acceleration is also positive because two negatives make a positive. When angular velocity and acceleration have opposite signs, your angular speed will decrease, such as if you are rotating counterclockwise and slowing down, that'll cause a decrease. If you're rotating clockwise and speeding up, that will also cause a decrease. In our next example, as the wind dies, a windmill that was rotating at 2.1 radians per second begins to slow down with a constant angular acceleration of 0.45 radians per second squared. How long does it take for the windmill to come to a complete stop? This is the equation you'd use, but I think it's sometimes challenging to imagine all these brand new variables that I haven't seen before. So if I imagine this as velocity, acceleration, time, and velocity, I can come up with this equation that I'm familiar with. And this equation that I'm familiar with is synonymous with this guy in a rotational reference frame. So that makes me feel a lot more comfortable. We can fill in our values, and we end up with 4.7 seconds. Our last example has riders at an amusement park moving in a circle of radius 10, executing an angular velocity of 8 revolutions per minute. The problem wants us to solve for our angular velocity and our centripetal acceleration. We already have an angular velocity that is represented in revolutions per minute. We just have to convert that into radians per second, because that's the standard form. So when I do so, I get 0.837 radians per sec. Centripetal acceleration is tangential velocity squared over r, and we know our radius is 10, but we don't have a tangential velocity. We do, however, know that tangential velocity is equal to the radius times the angular velocity. So if we multiply 10 by our angular velocity, that gives us a tangential velocity of 8.37. And when we solve for that, we get a centripetal acceleration of 7 meters per second squared. Nice work today.